In the last section, we are talking about energy more on a macroscopic level. For example, if I take a gram of wood and burn that wood, how much energy am I getting out? How much heat am I getting out? Now we're going to use this energy idea, but we're going to scale it down to the subatomic particle level. So we're getting really, really tiny. And we're looking at now individual packets of energy. So the smallest packets of energy that we can measure. And this is the idea of the quantum idea of energy, is that these are small, specific packets of energy. To introduce us to these packets of energy, they really come in this energy called electromagnetic energy. And all electromagnetic energy travels at the speed of light, which is 2.9979 times 10 to the 8th meters per second. So that's incredibly fast. They all have this wave or oscillation that they go through. They act as waves. So they have this fluctuation in intensity for their electrical and magnetic activity. And they have a wide range of different amounts of energy. So you can see on this diagram here, we can go very low frequency, where the wave is really slow and low. This is something that you might see in the radio wave frequency, the frequencies of a lot of cell phones, the either 3G, 5G, whatever the next iteration is going to be, LTE. That's all in this lower radio wavelength. We can move up a little bit more to microwaves, infrared technology. We start to see visible light and ultraviolet light. We start to see this higher energy wave forms here. X-rays and gamma rays are way higher energy. So these can all travel through empty space really fast, and they're really interesting because we can receive this energy through really long and far distances through space. This is how the sun sends the energy to the earth, is through electromagnetic energy. So in order to talk about waves, we have to provide a few different definitions for what they are and some of the properties of those waves. One of those things that we're going to be talking about is the wavelength. And you'll see this symbol called lambda. It's Greek symbol lambda. That is going to represent, anytime you see that, the wavelength. So it's the length of the wave. So the distance between two successive peaks or troughs. So this would be a wavelength, or this would be a wavelength. You can also, in between, you could start at the node, and that would be one wavelength. So that's here's showing you that lambda. This is the length of one wave. Typically, they're found in units of meters, centimeters, nanometers. Visible light, for example, is often given to us in nanometers, because it would be about 500 nanometers is going to be about where that visible light spectrum is going to be found. So it just gives us a good unit to work with when we're talking about things in the visible light spectrum. Frequency, this looks like a V, but it's kind of a more fancy V. It's actually the Greek symbol nu. When you see this means frequency, and this means the number of waves per second that pass a given point in space. These are often, the units are kind of weird for frequency. It's 1 over seconds, or seconds to the negative first power, which is the same thing. We're also cycles per second. And then the official unit that's more often used is hertz. That unit means per seconds. So if we have this on the left side, we have 2 waves per second. So it's cycles per second, so that would be 2 per second. So this is related by lambda times nu is equal to the speed of light. So if we have the wavelength, for example, we always know the speed of light is going to be 2.99 times 10 to the 8th meters per second. That's a constant. So we can always solve for the nu or the lambda if we have one or the other. A few other properties are, we have amplitude, which is the maximum height and minimum height. So the amplitude is going to be described by how high this peaks. And this is related to the intensity. So if we have more intensity or higher brightness of light, that means the amplitude is higher. It would also be analogous to a stereo system. If we turn up the volume, we're increasing the amplitude. Another point I want to show you are these nodes. These are going to be important when we start talking about electrons acting as waves. These nodes are important parts of where electrons would not be found. There's no amplitude or there's no amount of those at that point. So we'll talk about that when we get there, but this is the place where that waveform goes through the axes. I'd like to use some of the information that we just discussed in terms of wavelength, the frequency, the speed of light to solve this problem. And here we have the bright red color in fireworks is due to an emission of light when strontium nitrate is heated. If the wavelength is 650 nanometers, what is the frequency of this light? So the question is, what information do we need to solve this problem? I just gave you a really important equation where lambda times nu is equal to the speed of light. So what you need to know is, what do these things mean? So this lambda is the wavelength. Now I have in the problem, I'm giving you the wavelength 650 nanometers. The speed of light is a constant. It's approximately 3 times 10 to the 8th power. I a lot of times will just simplify that. Instead of 2.9989 times 10 to the 8th meters per second, I'll simplify that and get an estimated answer. That's fine for this one. Here I'm going to solve for nu. So I take this problem. If I divide both sides by lambda, I get c over lambda is equal to nu. So nu is equal to c over lambda. Now I plug the values in. 3 times 10 to the 8th meters per second is the speed of light, divided by 650. Now I've done a conversion factor. What I do know is that 650 nanometers is 9 zeros smaller than meters. And I need those meters to be meters instead of nanometers so I can cancel those units out. So that's one of the other things that we had to do here, is to do a conversion factor to convert this to meters. Those cancel out, and then I plug in the 3 to the 8th power times 10 to the 8th power divided by 650 times 10 to the negative 9th power. When you do that, you should get something like 4.6 times 10 to the 14th power per second, right? This second over here drops to the denominator, so it's an inverse 1. That's per second. That's also equal to hertz. Okay, so now it's your turn. Use that same equation. Now I'm giving you something as 880 kilohertz, and I want you to tell me the wavelength for that signal. So it's one of these 5 answers. I'd like you to work through that problem and post your answers in our Blackboard space. Again, as we saw earlier, we have electromagnetic spectrum, and there's this idea of different energies having really various amounts based off of their frequency. So we can see that we have different sections. They're comprised of different frequencies, and we look at gamma rays, X-rays, UV, visible, infrared, microwave, radio, television, cell phone waves are lower energy. And we can have this variability between them, and it's all based off of how quickly the frequency is happening, as you can see on the left side here. I want to start talking about this wavelength of light based off of visible light, because this is what you can see, and it's kind of a good way to start this process, to start explaining some of the things that we can see with our eyes. So the different bands of light that we can see with our eyes are between 400 and 700 nanometers. So they make up the whole spectrum of colors that is visible to us. When we combine all of the colors together, that's actually white light that we can separate out from a prism into the various rainbow that we can see, for example, when it's raining. That's essentially the same thing that's happening with a raindrop that will split apart and diffract the light into these various different colors. a little biology lesson, we have these different components within our eye that are actually neurons that can receive energy through light. And they do that through these cofactors that are bound by different proteins in our eyes. So we have rods and cones. These are cells. And within these rods and cones, there are proteins and these cofactors that are shown here called retinal. And they're bound by proteins. Those proteins then, when this cofactor is hit with certain wavelengths of light, depending on the protein that's bound, that will change the conformation of this structure. It'll go from a bent to a straight. That changes the protein structure. That protein structure within this neuron will then change and open up the floodgates for calcium signaling that causes a signaling cascade down through past the nucleus into the synaptic nerve endings, and those transmit the signals into our brains. So this is how this actually works. This is why we can see light that's at 400 to 700 nanometers, because this structure, this chemical, responds to only that wavelength of light and nothing outside of that. If we have different compounds or different proteins, that can allow other things to respond to different wavelengths of light than what we can see with our eyes. For example, snakes or pit vipers, they actually have these pits that are able to recognize infrared light, so they can actually see and sense heat signatures from rodents, for example, and they use that for for night hunting. And this is just a different protein and a different cofactor that's attached to different parts of their bodies. In their face, they have these pit receptors that are able to receive that signal. So it's just a small change, an evolutionary change that allows them to see that light. For this question, I just want you to make sure that you've gone through and kind of understand the differences in terms of the frequency and what that means, if it's higher energy, lower energy, and how we distinguish between these different forms of electromagnetic radiation. So I'd like you to list the following in order of increasing frequency. So going from the lowest frequency to the highest frequency. Post your answer in the Blackboard space. So we're going to start to talk about this idea of, when we were talking originally about things in the last chapter, the last section, we were kind of more looking at things working as particles. And those things work better if we think of matter as kind of a little ball, for example. Right? A lot of times we use the analogy of carrying a ball up a hill and then dropping it down the hill, looking for potential energy and velocity, looking at kinetic energy. But later we started to realize that some of these particles, some of these things that we are interested in studying in chemistry, were not acting quite like that. They were actually acting more like waves would act in this case. So we're going to start looking at these different types of experiments and some of the things that led people to believe and understand that these, especially when we start talking about electrons, are acting more like waves sometimes and like particles sometimes. So it's kind of an interesting phenomenon that we're going to look into here. Two of the people that started these ideas of looking at these particles or the photons or electrons even as waves or particles, they were Newton and Young. So Isaac Newton, around the 1700s, he decided that he thought that light was acting more like a particle. So all of the things that seemed to make sense to him at the time were that there was a reflection that was happening with light, there was refraction, and he didn't necessarily know about any of these other things below that. So interference wasn't something he was familiar with, diffraction, polarization. That was really before his time. Now, about 100 years later, Thomas Young, over here, started to look into this idea of the light being actually more like a wave function. And here we started to see, okay, we're still, with waves, they'd still be able to reflect, they'd be able to refract. Where the differences start to be seen is when we look at interference. Interference is this idea where once we have two waveforms next to each other, they can actually interact and change each other. If we watch a short video on this, so what we're going to look at here is a demonstration of the idea of looking at a compound or a light as a particle versus a wave. And here we're going to look at doing this through this process. So this is going to be where we're going to shoot kind of waves or light out, and we're going to pretend that it's a particle. Now this is what would be expected if we have a particle. Those little light beams are going to go through the slits and then hit behind on that wall. The next option is if we treat this like a wave. Now you can see what's going to happen is this wave's going to hit the two slits. Once it hits the slits, there's going to be actually some diffraction, which is the bending of light around. Once it hits here, this wave is going to bend a little bit around, and then it's going to interfere on the other side of this. And we're going to see what happens when we have interference. You can see the pattern on the other side is different. That interference is causing these things to come together and add, and we're actually getting different pattern on the wall where we have higher intensity hitting and causing this red light to form, and then we have some areas of interference where there's no light actually being shown. So this is kind of the idea that we're looking at with interference, was this kind of new idea. And we also have this idea of the diffraction, and just a second, we also have this idea of diffraction, which is where that particle is going to bend around that door again. So we talked about looking at bending those things, diffracting them. Once it hits that door, you can see the solid objects just kind of went straight through, but the light kind of bent around on either side of that opening. We can also do this polarization. So you maybe have polarized sunglasses. It's the kind of same idea. If you have a particle, it's going to be traveling in one direction, but the waveforms can travel in multiple different directions. And so this limits, basically little slits will only allow certain amounts of that going in the correct direction to go through, where a particle would go through no matter what. And finally, the photoelectric effect. This is the final thing that we're going to look at. Photoelectric effect is this last idea here, where it seems like Young's plan was all going well until we hit this idea of photoelectric effect. And this is where Einstein comes into play. And this is where it actually acts more like a particle, because we have this idea where we need a certain amount of energy. If in this little figure over here, the idea is these green little blobs here are going to be our protons in our nucleus. The red dots here are electrons. If we hit this compound that is made up of, maybe it's a metal sheet, for example, we have electrons in here. In order to eject electrons off of here, we can actually hit them with a certain amount of energy within these photons, and they will eject these compounds off. Now, if these are acting like wavelengths, this doesn't work as well, because we should be able to just increase the amplitude, increase the intensity of the light. But what actually matters is the frequency of the light, not necessarily how much is there, but the energy within that. So this is actually more working like a particle, where a certain amount of energy and the mass has to be involved in order to eject an electron off. So Thomas Young's idea kind of falls apart. It's not until Einstein in the 1900s, about again 100 years after Young, where this is kind of determined and figured out. So we need to get into some terminology here. And again, we're going to introduce this idea of quantum energy or quanta of energy. This is also, we also describe these as photons. So that's the same kind of idea. Is a photon, a single photon is a unit of energy. Photons travel with the velocity of the speed of light, so about 3 times 10 to the 8th meters per second. The frequency, the nu, is going to be a certain frequency for that photon. And the energy of the photon is related to Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. This allows us to convert that frequency, that new value, directly into energy. So it's just a conversion factor. So we can multiply this by the frequency and it tells us how much energy we get out. The big unit that's new here is joules. So this is the same idea of joules. We can also go into calories. That's another unit of energy that is often used. So joules and calories are kind of the same idea. They're similar to the difference between feet and meters though. So now we're going to solve some problems with this new equation where energy is equal to Planck's constant times the frequency. So the information we need to solve this type of question where we're asking for the frequency in seconds to the negative 1, that's the same as hertz, of radiation, which has an energy of 3.371 times 10 to the negative 19th joules per photon. So here I have rearranged this from the energy is equal to h times nu. So now I've just divided the energy by the Planck's constant, and then we just need to know what Planck's constant is, 6.626 times 10 to the negative 34th joule seconds. We can start plugging and chugging those values in. So this is the energy that I've given you in the description here, joules, and divide it by Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. The joules are going to cancel out, and you'll notice that the seconds, the inverse seconds, are going to be left. So seconds to the negative 1. If we divide these values here, we will get 5.087 times 10 to the 14th per seconds, or hertz. Now it's your turn. So I want you to use that same idea to put together the answer for this question. It should be one of these 5, and set this up and post your answers in the Blackboard space. So from the earlier calculation, so we were looking at a red colored firework, and we had 650 nanometers of light. When strontium nitrate is heated, what's the energy of one photon with this wavelength? And then what's the energy of a mole of photons with this wavelength? So the first thing you have to do is go back to that other question, and I'll just remind you that the frequency was 4.6 times 10 to the 14 hertz. And then you'll use that energy equation we talked about, and we'll determine the energy for one photon, and then we have to use Avogadro's number to determine what the energy would be for a mole of photons. Your answer should be one of these 5. Please post your answer in the Blackboard space. So now I'd like to revisit this idea of photoelectric effect. And here again is this idea: if we have a piece of metal, potassium has protons, electrons in here, neutrons, but really what we're trying to do is we're trying to hit it with enough energy to actually eject an electron off of it. And the interesting thing here is that when we have a certain frequency, if it's not high enough energy, the frequency is not high enough, then nothing happens. So this red light has a lower energy than green light, for example. If I can hit this potassium with all the red light I want, and I have as much amplitude as I can crank it up as bright as I want to, it's not going to eject an electron. But when we get above a certain frequency, when we hit the green spectrum, for example, I can hit this and eject an electron off. And in fact, if I find something else like blue light or violet light that's even higher energy, I can eject that off with higher velocity as well. So instead of 3 times 10 to the 5th, I get 6 times 10 to the 5th meters per second of ejection speed from that electron if I hit it with higher energy. So there's this idea that we can increase the intensity, we'll increase that speed at which we can shoot that off, and that's more acting like a particle at this stage. We can determine, we have to basically get enough energy. Planck's constant times the velocity has to be equal to or greater than the binding energy of the electron. So there's the electron is bound to the proton in this piece of metal. if I hit it with enough energy, then I can eject it and I can break that bond. So here's a quick little video kind of looking at this idea of photoelectric effect, and just to give you an idea of this in, how it's going to be shown here. So for the setup here, there is a light source. It's shining into a detector. This detector is showing you in the screen here the multimeter, which is really high right now because it's hitting it with all the intensity of this bright light. Now he's going to place this red element in here, and we're actually going to see that we get a decrease in the multimeter rate, and this is going to tell us basically how much of this light is able to eject photons. So we don't get any ejection of the photons when we put that red glass in there. Now he's going to replace this with a different color. We're going to put yellow light in there, and we hit this compound, we get a little teeny bit of energy of electron flow going in there, and now he's going to use the green light. We see a little bit more, about 3 for the multimeter, and now finally at the end he's going to put a blue or a purple glass in there, and we're going to be able to see that this is increasing in intensity. So we're close to 6 or 7 here. So that's the idea of the photoelectric effect and how we can use that idea to understand how particles, or how these photons are acting sort of like particles, but also we're going to talk about how they're acting like waves as well. The photoelectric effect also tells us something about energy, and it tells us that there are certain thresholds of energy that must be met for things to happen. And it also means that packets of energy have a specific amount of energy, which means it's quantized. So this is the idea that these are some examples on the screen now of analog versus digital systems. So the clock here, this is an analog clock. Here is an analog voltmeter versus the digital versions underneath. Where the digital, it's clear what time exactly it is, where the analog version, you kind of have to estimate those digits in between. So it's 2:20 right now, or is it 2:21 or 2:20 and 30 seconds? It's harder to tell with an analog system. But with digital, it's very precise. It's telling you exactly what those numbers are, and there's less ambiguity there. Another picture of kind of this idea of analog versus digital is this continuous pathway for this rabbit coming down from high to low. And on the right side, it's unambiguous. This rabbit is on the second step, and we know exactly where it is. And kind of going back to the analogy of potential energy and kinetic energy, we know exactly how much, the distance this is from the floor, because we could just measure that step from the floor. Versus where is this rabbit here, it's harder to tell because it's on a slope. So this just simplifies this process. This quantized energy means that packets of energy have a known specific amount, and it's unambiguous. We know exactly how much energy that is, based off of our understanding of Planck's constant and the frequency of that packet of energy. When looking at photons or electromagnetic radiation, these are all quantized groups of energy. They occur in discrete units, as I mentioned, which have the size of Planck's constant times nu, or the frequency of that photon. One photon is equal to a quantum of energy, and again it's gained or lost by this ratio of the number, if this is a whole number digit, multiplied by the Planck's constant and nu. So if n is 1 mole, that's Avogadro's number, that would mean the energy of a mole of those photons would be equal to 6.022 times 10 to the 23rd Planck's constant times nu. So if light is required to start a reaction, we have to have that light above a certain frequency so that we can get a certain amount of energy out of that. And anything below that minimum threshold energy, the intensity isn't important. It's the overall energy that's important. So the number here isn't important for that overall energy. It has to be the right frequency as well. Here's another example of that case where we need to hit a certain energy threshold for each photon. If you irradiate plants with infrared or microwave radiation, which is lower energy than visible light, no photosynthesis is going to occur. So this would be, in this chart, this is the wavelength in the x-axis in nanometers. So we have 400, 500, 600, 700. We have light in the ultraviolet range, lower than 400, blue, green, yellow, red, and then infrared is above that, around 700 or higher. So if we irradiate plants with infrared light, nothing happens. We don't get photosynthesis, and those plants would eventually die. However, you'll notice this chart, in the normal range, not infrared, but just red light, it does absorb red light. It also absorbs light in the ultraviolet range and beyond. You can see in the violet and ultraviolet range, there's still some absorption. So this is where we have the those photons of energy. They're responding, they're interacting with the chlorophyll, and what's left is this green light. So that's why a lot of plants look green, because it's not absorbing that light. So this kind of tells us something, that the wavelength, the specific wavelength of light, is really important. It's kind of the same idea as I was mentioning earlier with rods and cones and retinal and your ability to see light with your eyes. We have to be able to hit with a certain frequency of light, and that's what's going to change the shape of that cofactor we were talking about earlier. Now I want to look at using this idea of photons and packets of energy to identify the energy contained in 1 mole of photons with a certain frequency here. So again, we have to pull out our equation where we have energy is equal to, this is Avogadro's number because this is where N would be 1 mole, and then times Planck's constant times nu. Here's the frequency. Of course, I don't have a unit on here, but we know frequency is given in hertz or per seconds. So I can plug in all of these numbers because I know Avogadro's number. We know Planck's constant is always the same number. And then the frequency is given above here. And then I've put the units in per seconds. Now we can just plug this in. We can cancel out our units here. I'm sorry, this should have come up as the seconds, subtracting the per seconds, not the joules. Sorry, they got moved over somehow. And then this will end up giving us a joule per mole. That's the unit. So 7.98 times 10 to the third joules per mole. So that is how we would solve this problem. Now I would like you to look at a mole of photons has an energy of 1.6 times 10 to the negative third joules per mole. What's the frequency of each photon? So we go back and look at that last question, use that same equation, but we have some different numbers to plug in. So solve this problem and post your answer in our Blackboard space. Fireworks are an interesting way to think about how this is working and how these different wavelengths of light are involved in this process. So we can actually get electrons in these compounds. So with calcium salts, barium salts, strontium salts, copper compounds, sodium salts, and the electrons in those compounds get excited when we explode. We light these things on fire, they shoot up in the air, they explode, and that the energy gets transformed in the electron and it goes into this excited state. It stays in that excited state for a short time, and then it relaxes and goes back down into the normal state. But as it relaxes, it has to release that energy somewhere, and it can release that in photons of very specific wavelengths of light that you can see as orange, yellow, green, blue, purple, red light from the fireworks. So this is a kind of looking at this idea. This is what's happening when the explosion happens. We have ground state electrons. We have a certain amount of Planck's constant times the velocity. That specific amount of energy is put into the electron to bring it up to an excited state. And then after a short time, those electrons can go back down and release the energy as that same amount that it was excited in. So it'll drop back down into the ground state and release that energy. So it's absorbed in those specific amounts of packets of energy, and it's released in those as well. And there might be multiple steps within this excited state or that relaxing state. So you might have different colors that released or different wavelengths of light or electromagnetic radiation that's released as that's relaxing. Some of them are likely in the visible range, as we could see with those fireworks, for example. So how can we visualize this relaxation of that excited to ground state? So we can look at different colors through, if we're looking at that happening with white light, we can break that down into visible light through a prism. For example, sunlight is doing that. Incandescent light bulbs, however, those will do that with that'll have white light, that'll have all of the different colors. Very hot metal rods will be white. But we can also do this with certain gases in a bulb. Here's an example of if you basically make a light bulb with hydrogen gas. This hydrogen element has an electron, and the electron can be activated into a more excited state, and then it can move back down and relax to a ground state, and it will actually give you 4 different bands, 4 very discrete and defined bands in the visible light range. This is going to be something that we can look at, and we can study this and understand what is happening, and we can have a little bit more understanding of what's going on with the electrons in this hydrogen gas. So this is what we'll get. And what's actually happening again is, as we're putting electricity through here, we're able to excite the electrons into an excited state, and then as those are relaxing, they will release different wavelengths of light. So we can study that and understand now where the electrons are, how they work, and what is going on with how they're organized here. And this is kind of what you can do with various different gases. So this was done with hydrogen, we can do it with helium, we can do it with some of the different noble gases, where you basically take this light, you send it through a prism, and then that prism will break that light up into these different forms so that you can see all of the different wavelengths of light for the color spectrum here. So different gases will give you different colors. Here's just an example of the different light colors from various different gases. And down below you can kind of see where helium might light up, or neon will have a couple different line spectrum, krypton, xenon. So you get more and more of these. So hydrogen is the simplest single electron system, but when you get into bigger and bigger and bigger molecules, they get a lot more complex. And there are different equations that explain this, and the mathematical equations that will actually explain where these electrons are coming from and what kind of wavelength you're going to get. So this is one of them, and I don't want you to get too worried about this. We're not going to spend too much time working through this, but it's just an example to show you how math has been utilized to understand what's going on with electrons in these systems, in these atoms. So the Rydberg constant, just to describe what this equation is telling us, is 1 over the wavelength is equal to this constant, which basically is a conversion factor from wavelength to these different numbers that we're going to look at. They're basically the registers or the steps between those different quanta of energy. N1 and N2, they have to be these numbers here in these denominators of these two ratios. They have to be whole number integers, starting with 1, anywhere from 1 to infinity. So we don't have to start here with a 1. It could be a 5, just as long as this is increasing in a larger number. So these can be used to calculate the wavelength of the spectral lines of hydrogen. The Balmer series in the Rydberg equation is where n is 2 and then anywhere from 6. And these are all of the visible spectrum light, those 4 different spots that you can see within that series is going to correspond with those 4 different wavelengths that we saw earlier. Here are what the Balmer series, it would be able to describe exactly the wavelengths that are shown in these 4 spots. All right, so let's look at this question here where we're looking at where n1 is equal to 2 and n2 is equal to 6. So if we have an excitation to n of 6, n2 of 6, and then it relaxes back down to 2, what is the wavelength of light we're going to get out of this? So what we need to know is this Rydberg equation where we have 1 over the wavelength is equal to that Rydberg constant and then multiplied by this ratio minus the second ratio with those corresponding numbers here. Rydberg constant is 109,678, so 109,678 centimeters to the -1. So this is, remember, this is going to allow us to convert here. So this is a unit that we need to put in here so that we get the wavelength will be an actual length. Here I've plugged in the values into the Rydberg equation where we have this 2 is being squared, this 6 is being squared. We're going to subtract this ratio by this ratio. I've simplified this over here. 2 to the second power is 4, 6 to the second power is 36. And then taking this 109,678 centimeters to the inverse 1, multiplied it by this ratio of this subtraction product, and then I get 24,373.9 centimeters to the inverse 1. Now this is important, right, because this is an inverted centimeter. This isn't a normal length yet. That's because this is 1 over wavelength is equal to this. So I'm going to basically multiply both sides by this, this lambda value and then divide by the 24,000 number. Now I'll get 1 over that value, and then the centimeters to the inverse 1 will come up to will not be in the denominator anymore, and then we can solve for that 1 over value. So we get about 4 to the negative 10 times 10 to the negative 5th, and then I can convert that from centimeters to meters and then meters to nanometers. It's just easier to sometimes convert from meters if you're getting smaller. So overall, once we've done this math, then we should get the wavelength of about 410 nanometers, and that is one of the lines in the violet area of the spectrum. So I'd like you to use that Rydberg equation to determine the lambda for a series where n1 is equal to 2 and n2 is equal to 4. So we're going to excite this to the 4th level, and then it's going to resolve and relax down to the 2nd level. And tell me what the wavelength is going to be. Post that in our Blackboard space. So this starts to bring us to the Bohr model of an atom, where this is kind of the first theoretical model of the atom to successfully account for the Rydberg equation. It's not quite perfect. We're going to improve upon this model, but one of the first things that we looked at originally was this idea that we have these different shells and these different spaces. So this kind of helps to understand that, thinking about the protons and the neutrons in the middle, electrons floating around the outside. This is kind of the quintessential idea of an atom that has been universally shown to be how this actually works. We're going to talk about this. This isn't quite true, but it does help to understand and start to explain what is happening with the Rydberg equation and these different steps of energy. And so this is another way of kind of looking at this energy. It's more complicated than this, but this is kind of the initial idea that we have been able to develop from this idea of the Bohr model here. We have the nucleus in the middle, and electrons are in these different shells around the nucleus. These red lines are showing you where we might be able to accept and absorb energy and go into these excited state shells. So the relaxed state, the lowest energy level state, is where n is equal to 1. And then we get into these higher levels of kind of thinking about what we were just doing with the Rydberg equation, where that n jumps up and gets a higher energy level. Then we can come over here and we can go to different levels back down. We can go just like you might take a stair, we might jump all the way to the bottom, or we might just jump to the second, or we just might walk to the first. We might start on the second stair and do any of those combinations in between. So all of these levels are quantized. They're going to give you different wavelengths of energy out, and that's going to sometimes correspond with visible light here that we can see in this spectrum down below for hydrogen. As I alluded to earlier, this model starts to fail because the theory doesn't explain what happens if you have more than one electron in an atom, right? A hydrogen's simple. You have a proton, you have an electron, and it's really easy to see what's going on. But there are more complex systems that this doesn't then follow. And we're going to talk about that kind of in the next part of this section, where we start looking more closely at how to explain where electrons are. And we now have to start talking about electrons more as waves and less as particles, because the Bohr model really treats an electron as a particle. But we know from some of the earlier discussion that that's not necessarily true, and that's not necessarily how these things are happening. So it's more complicated than that. The theory also doesn't really explain this idea of the collapsing atom paradox, which means if we have something as simple like we're looking at a proton in the middle and an electron orbiting that proton, it's too simplistic, because what we never see, what we don't see, is an electron ever collapsing into the proton and then kind of fusing together. That doesn't happen because electrons act as waves, and they're going to be in certain places that they're going to not ever be in certain places. We're going to talk about that when we talk about nodes and where we don't find electrons in just a moment here, or in the next section. So we don't see that, and this model doesn't explain why these things don't collapse in on each other. So finally, I want you to kind of think about this. If we're looking at, for Bohr's atomic theory, when an electron moves from one energy level to another energy level, more distant from the nucleus, which of these following statements is going to be true? So post this in our Blackboard space, and this concludes this part, and then we're going to go into more discussions of electrons and energy and how they change their shape, how they act more like a wave.